you have this electron. Okay, I got it. So so basically now in this last class you have this kind of say diamagnetism driven by electron-electron interaction. Okay, so check. So now, okay, that was some kind of example, and as I said, this one of the success of UHV chemistry is that basically now these molecules, which were dreamed by chemists for a long time, and it was very difficult to synthesize them because, of course, these are radical molecules, and it's very difficult to stabilize them in solution. So, but now with this on-surface chemistry plus the high-resolution imaging, this triangulin was demonstrated that it can exist, and then this Clark's goblet, and recently also some acids, which now I think the longest one is 15, and also the let's say this pi-magnetism derived by electron-electron interaction was also demonstrated. Also what is called the rhombenes. So what I'm gonna touch in the first part is actually this. So that's another approach which I would like to discuss here, and that's actually introduce this this magnetism by electron-phonon interaction, or you will see this is also related to somehow transition from topologically trivial to non-trivial. And then I would like to show that in the second part that basically what we can do is we can combine different approaches, because so far here we have been talking mostly about the biradical, so 2 unpaired electrons, but combining these two strategies, probably we can go to the molecules which are strongly correlated and having, for example, tetraradical character. Okay. So to start with, the first one, I think that probably, I will. It's interesting to show that actually in solid state physics, if we are talking about topological state transition or phase transition, that was already known, or it's somehow related to what the chemists talk about, And if you come from the chemist part, then basically one of the things, and again, these are like, where the solid state and chemistry meets. So when we start with one-dimensional system, because here in this case, I'm gonna discuss like this p-conjugated polymers. So if we know that about 1D system, so one signature of 1D system is so-called this spiral transition. So if we have a 1D chain where each side has one electron, the Pyrals actually and others, they discovered that basically these chains are unstable, the metallic chains, and then you have this Pyrals transition or dimerization, which opens the gap. So there is a competition between the gain energy and electronic structure, and then there is, of course, the penalty for the distortion, but always, according to Spiral's theorem, always let's say this semiconducting phase is more favorable. So then in the chemistry, what they call it, so what is called is bond length alternation. So if you look at this, so the people have been looking in chemistry to create something like cumulin, which would be this carbon chain made of equally distant polymer, but always they see that due to the Pyrals, you will go to something like this, which is called this ethylene, so that you have not combination of this double bond, but you will have a simple triple simple. And also there is some rule where basically the difference in these distances here tells you how big the band gap is. So there is some correlation. If this alternation or bond length alternation is larger, then the band gap is larger again. And in principle, if you would be able to stabilize the cumulin, then for this infinite chain, you will get again the metallic case. But we know from Pyrals that basically this is not possible. Okay. Then one more thing is if you look at the molecules, again, that's very interesting. Again, look at this. There is some interplay, about electronic correlation and these bonds, how we will adjust them, and the chemists, they typically can draw, for example, this molecule and different schemes, like how to establish these bonds where each node would have like four connections. Here there is a hydrogen, and of course you can go from this closed shell, which we call it aromatic, and then you can also draw some scheme where you have 2 unpaired electrons, which is called quinoid. And what was also discussed in these p-conjugated polymers, that actually the transformation from aromatic to quinoid is related actually to the switch of homolumo. So typically, if you go from one resonance to the other resonance form, what happens is that homolumo will switch. So that basically when you go very close to each other, then the homolumo is in single electron picture, homolumo is approaching, and then they switch. So that was discussed by Miklos Kertész in this paper, where they shown actually that this transition from quinoid to aromatic is driven by the crossing level. Yeah. So yeah.
Could you tell me how large is this typical gap in such systems? I don't know. I mean, electron volt, hundreds of electron volt.
It can range for small molecules because you have strong. Okay, then also the electron correlation plays a role. So typically in benzene you have like almost like 6-7 eV. Then now, of course, what we are talking about, if it's optical band gap or transport band gap, but let's say in single DFT, let's say 10 eV could be. But if you go to larger molecule, of course, the band gap is shrinking, and in one moment you could have this transition to open shell, and then this will be. So typically, if you have a molecule in molecular systems, we can talk also about, let's say, half eV. But these start to be already molecules where, again, the picture is not so simple, that basically these two resonance forms, they will start to contribute to the ground state somehow. So and then it starts to be more complicated. But again, like from the point of view of solid state physics, if you look at these guys, you can see it more like this problem of charge density waves on the surfaces, because this bond length alternation means that here there is a more charge location and here there is a less charge location. So again, you can find some similarities when we are talking about the charge density waves on the surfaces. Then you could talk also about charge density waves in these molecules, due to these short, long bonds. Okay, so now I think that's just very brief remind. Now this is where the topology comes from, and that's already the Su-Schrieffer-Heeger model, which is, I don't know, 30 years old and maybe older. And I think this is very nice example, very simple example how to introduce this topology in 1D. So typically, if you will get this polyacetylene chain, you can mimic this. We already assume that there is this spirals distortion, so we have a chain where you alternate simple and double bond. And now, if you will make the infinite chain, actually now it's you can shift arbitrarily this unit, and in principle, if you look at the electronic structure. So that now what I'm doing here is basically I will just shift this unit here, and I can do it in the same way that I will change the strength or ratio between T1 T2, which is the hopping which I'm varying. So for the double bond, the hopping will be larger because it's shorter, and then for simple bond will be smaller. And now I can gradually, at least the mathematical way, I can just tune this T1 T2 limit. So if T1 T2 is not equal, you will have the band gap opening. If I meet the criteria T1 is equal to T2, it means basically there is no bond length alternation. So then I will get this metallic phase. And then again, if I will switch now, and in this scenario, this one becomes simple bond and this one becomes double bond, I can recover again this gap structure. Now, if I'm in infinite chain, actually, there is no way in principle, if I look at the electronic structure, if I will keep the ratio T1 to T2 the same, I will swap between them, you will find the electronic structure exactly the same. So, and that's I think like 20 years ago, the solid state physics was this kind, I have electronic structure and nothing behind. So I would say these two things are equal. But then when we go to when you start to analyze this, and you will realize this is not exactly true, and here you can write this Hamiltonian in this way, and that's this very nice example, which is also could be found in this book, is where they define this Winding number, which is this topological invariant of the system, and you will find it actually from topological side. This Winding number for these two cases is different. what does it mean in reality if I go to the final system? Means that in one case, which is this red one, it's topologically trivial, and then for the other one where the winding number is 1, for the green one, actually it's topologically non-trivial. What does it mean for the finite chains? Again, there is nice example. If I go to this fully dimerized case, what I can see is if I go to this kind of example, which means the red one, you see that these double bonds, they will pair perfectly, so then I don't have any, let's say, electrons, unsaturated electrons left. On the other hand, if I go to this green one, I just order this double bond in other way. Now I will see that actually 2 electrons remains unpaired, and this gives origin to this zero energies edge state, which is signature of these topologically non-trivial states. Okay, so that's just, you know, very brief example. So what is important now? So we can, if I go here, I can see that this is kind of like quantum phase transition, because here this is not related to the temperature, it's related to, let's say, some property of Hamiltonian, where I tune one parameter and I can drive the system from one topological, let's say, topologically trivial to topologically non-trivial state, and there will be some impact on the final structure. And so first thing is the proximity of this phase transition modulates the band gap. Yeah. So if I'm in topological non-trivial phase, I should observe this zero energy edge state, and I should also see the swap of these Frontius orbitals, at least in this one electron picture. Yeah. And so idea is now, okay, can we find something, some similarities, or can we go to something realistic here? So that's our proposal. We're gonna look at these polymers, which are made of Ascene units and connected with this ethylene bridge. Yeah. So now, if you look at just the monomer, so that the monomer would be Ascene, and that for certain case you go and you see the monomers. Of course, this increasing size of the monomer, you will be decreasing monotonically the gap. However, what I want to show here is basically when we go to the polymer, where I connect this Ascene unit with this, let's say, ethylene bridge polymer, we will see that actually at certain moment there is a phase transition. Yeah? And it will depend on number of these benzene units in this Ascene block. So first of all, what you can do is just the pure theory. And again, this is the time binding method where we also calculate the Zach phase for this infinite chain. And indeed, you see when you start with this polymer, which is made of benzene and then anthracene, pentacene. So you see at one moment you will, according to this time binding calculation, you will get perfectly metallic case, and then the band gap opens again, you know, and then according to this Zach phase, you can see that actually this start to be topologically non-trivial. Then you can do more sophisticated calculation using DFT, full relax, and again you see the same tendency. Okay, so now the question is, can we grow it somehow? And that's where we have this collaboration from people from India. They come up with this precursor and also idea to grow this on surface synthesis. So they use these precursors. So this is like anthracene, and there are 2 bromines on each side. Now you put it on gold, and there is so-called Ullmann coupling, which is very well known in chemistry, that these 2 bromine atoms, the carbon bromine will be broken, and then you will have here 2 radicals, and the system start to polymerize. And you see that actually this reaction surprisingly is going very well. So we can grow very extended polymers up to, let's say, 100 nanometers. And then, of course, we use this high resolution imaging, and we can really confirm the quality or this chemical structure of the molecule, of the chain. And here I would like to point out actually this bright spot here. So this is the AFM image experimental, and this is the simulated one. And actually here these bright spots tell you that actually this is signature of triple bond. So here we know that the chemical structure or chemical picture should be like this. Okay. Then now I told you that we have been telling that if you go from the anthracene to pentacene, so instead to using the precursor of 3, we will have also precursors of 5. And then indeed you see the difference. So for anthracene molecules, we do not see any H state when we go to the end of the polymer. However, when we go for this pentacene one, which again we can grow extended polymers, but at the end, if you look at this, you will start to see signature of this H state at 0 bias. Yeah. And what is so that's kind of like signature that basically this is the topologically non-trivial case. The other thing is,
Can I interrupt you?
Yeah, sure.
Is it possible to have these domain walls when the double bond, for instance, they repeat, and the
You mean well, you mean this kind of thing. So yeah, that's a good question. I would not say that here we go for purely like cumulin light. You know, in DFT, what you see is basically that still it's like ethylene bridge like, but this bond length alternation is not exactly like the same, you know. So we do not see any moving walls like solitons that this chain. The interesting stuff is that actually if you look at this H state is not, this brightest part is not located exactly at the end. It's more like, you know, 2 units away. And if you look at in DFT calculations, actually you will find that here this triple bond character is more strong than here. So there is still some kind of, you know, it's a good question, but I would like to point one more thing, but probably it will complicate it, you know, because we say that typically if you go to this SSH model, so this zero, they assume that the zero energy H state is in middle of the band gap, okay? However, here, this, you know, this SSH model doesn't take into account any correlation. But here, if you do, for example, a simple DFT spin polarized, actually you will see that this H state will not live in the middle of the band gap, and due to electron-electron interaction, you will split it. So there will be occupied and unoccupied state, like sumo, if you want, you know, due to the correlation. So what we observe actually here, because now we see the peak in the bias, in zero bias, this is related to the fact that we have a metal underneath, and there is a Kondo screening effect. Okay, so that's not what we see here is not the proof that basically we see zero energy state in the middle of the band gap. What we observed is the Kondo effect of, let's say, this fully occupy one single electron state at the edge. Okay, the one more important thing is I told you that this phase transition should be related also to the swap of HOMO and LUMO. And now, of course, here we do not have direct access. What we have here is actually we can calculate these DIDV maps. So this is the experiment and the theory. So this is the occupied band, and this is unoccupied band. So then here is the simulated image from the calculated band structure. So there is some selection rules. But interesting stuff is actually if you look at these two molecules, and I will come to this here, you see actually that now the character of them, it's swapped. So for example, for occupied states, I had this kind of structure which now looks more like this, and this unoccupied for the other one it has this character. So they swap. And again, I mean, this could be more clear if you look at, so here these are the simulated DIDV maps, and this is corresponding states, let's say in this K point here, you know, and now you see that actually the character where in this anthracene unit, you have the important thing is that you have bonding states on this ethylene bridge. In occupied states, in unoccupied states, there is an antibonding character, and now these two guys they swap. So the bonding character here, the state becomes empty or unoccupied, and this one stays occupied. This also tells you why this triple bond becomes weaker, because this bonding character of triple bond now is weakened because the occupied or bonding states of triple bond is empty. So this is another example again that this picture what the people have been using in chemistry, the swapping of these frontiers orbitals, it's also happens here. And it's also related to the fact why you change the Zach phase, because the parity of the states when these two are crossing then the Zach phase is gonna change. Okay, so I already said that this is kind of this quantum phase transition, because this phase transition is driven not by temperature, but is driven by, but let's say by some parameter which you change in your Hamiltonian. And in this Hamiltonian, important, this parameter, this function G, is not changing the spectra. It's only, well, it's not changing the character of spectra. It's only reshuffling these states, you know. So now the question would be, okay, in previous case, I told you we had some, let's say, stepwise transition, because we could not go gradually through this quantum phase, because otherwise you have topological trivial states, which is made by this polymer, which is made of this anthracene units, 3 units, and then you have a jump and you go to this 5 units. So now the question is, could we go really gradually through this phase? And the question is, of course, yes. What we found is actually, when we look at these pentacene ethylene bridge molecules, now what we see is that actually the phase transition depends on the length. So if we grow, if you look at the molecules or polymers which are short, we see there is no signature of this edge state. However, when we go to polymers which are longer than the 26 units, now the edge states, they emerge. Okay, and again, so that's perfect example where actually we can now look at and tune it and look at how the phase transition gradually goes. So to do that, actually what we have done different scenario, because one thing would be that very lengthy analysis that we would go for and sharing for this or searching for these different kind of different polymers, but you can do it in other way. You can grow very long polymer, and then what you can do is you can actually admit the hydrogen in the system, and what happens is that you see very long polymer, and now each of this side has a weird stuff, and this weird stuff is because this extra hydrogen passivates the polymer. So this of course modifies the polymer, but what we can do is later on is that we can use the pulses and we can shave again the polymers and going back to to this original form. So basically what you do, you come up with STM tip, you run the bias, and certain bias you see small jump, and then 2 hydrogens, these extra double hydrogens, they disappear, and you recover basically the pure polymer which you had before. So with that, you can go and now you can start to shape the polymer and prepare the polymers of different length. And so what at the end, what you can do is, because I told you if the polymer is short, then it means it will be topologically trivial. And if I have a polymer which is extended, then it should be topologically non-trivial. So here, basically what we have been doing, we shaved one part of the polymer, which is here. Then we had some, let's say, gapped polymer, which is still with this hydrogen. And then we had another segment which was free of this hydrogen, which should be now longer enough to be topologically non-trivial. And now you can do this STM and low bias voltage with the same tip. So now the advantage is that you can do it in once. So you see that so this short length polymer doesn't have any signature of these edge states. And now in these long chains, you do see. What is also nice, now we can go to these edges of conduction and valence band, and indeed, again, you see now this perfect swap of this character of conduction and valence band. So you see in the short polymer what was conduction band, so this presence on the edges, now it appears here, and then the other one is vice versa. So that's now with that you can play, because this is kind of easy, and you can really make very good statistic where this transition happens, So now this is the summary. So here you see how the band gap of the polymers evolves, this number of monomers. So that's basically we measure the DIDV, and then you see in one moment the band gap is saturating, and then this transition happens, and again we can also see the slope of these two conduction and valence band according to the length. So now, sorry, the question is, what is behind of this? What is the driving force of this? And what we believe is actually this is what is called this. Yeah, sure.
You So there are topologically protected states, but there are also localized impurity states that can be in principle in a system. If you have, I don't know, charge impurity nearby, it could attract electrons. Do such states exist these states are very popular in semiconductor systems. They always present. Do such states exist in these molecular systems?
You mean like you wonder if this X state would disappear if I would kind of charge them, or?
No, I mean that the systems are typically dirty and there are some impurities around, and I know just from naively I would expect that you will have something else. Just
well, that's a good point. I mean, here for a chemical point of view, these states are radical states. So if I would admit this polymer to the air, and actually I will see chemical reactions, I will probably see that these states will be quenched. So that's also some question, you know, when we talk in solid states that this is robust state, they are protected against the, let's say, disorder. I would say here, from chemical point of view, these are radical states, so they are very reactive. This is what you had in mind. So that's, to me, is kind of like dichotomy, you know, that.
And so when you say edge states, I always have in mind that there is, I know, you have a physical edge, but here you have transition between two different states. Just semantically, I would call it domain wall state. It's not.
Well, but you can define here this Zach invariant, and you know, when you calculate the mass structure, you see that these two guys basically change. So I think, you know, yeah, that's interesting. We can discuss, but I mean, domain wall here, I would go then you go more to solitons, you know. I would say that for me, the soliton, but you cannot move this guy here. You know, we have another work now which will come soon about the solitonic states, and again, there we do not see them moving, but probably the moving would also require certain temperature or things like that. But again, these solitons at the end, if you know these polymers, if you will expose them to the air, I think these solitons these are radicals, so they are very reactive, so they will be quenched by, for example, I don't know, hydrogen, oxygen, whatever. So that's something, you know, which now if you talk really about like the real materials which you consider in solid state physics, like these real semi-metals, I'm not sure from chemical point of view how robust they are. Yeah. So, but in principle, for example, here, if I will introduce some disorder, but mathematically in the T1, T2, in the hopping, you know, I would still keep it there unless I will go through this, you know, changing completely the T1, T2, that it will go to the opposite phase. Then it will start to be mass. But if I will just vary the T1, T2 on one side of this topology, the state would be protected. Yeah.
Okay, thank you.
Yeah, welcome. So now what I would like to show you, what we believe is that basically what is behind of this phase transition is this pseudo Jahn-Teller. Okay, so the pseudo Jahn-Teller is that always exists in the system, and now the question is how it's strong. So it's electron-phonon coupling. So in principle, if I look at this in this potential energy surface, if the system is stable, so let's say the second derivative with respect to some displacement, it should be positive. But then what I have is I have this, let's say, vibrational mode which connects me, let's say, the ground state with any excited state through some electron-phonon coupling, and this could be source of instability. Okay, so now I hope that this works. So what I can what you can see here, if I start to increase this electron-phonon coupling, in one moment the system, the Q is kind of displacement of the system. And now if I start to increase this electron-phonon coupling, in one moment, I will get the new minima, and this is also like this phonon softening in solid state physics. So basically here what I can say that I have one, let's say, bond length alternation, and if I will start to increase this electron-phonon coupling, in one moment I can have some phonon softening, and I can go to the new state. So now if you look at this theory, there are two things which drives this pseudo Jahn-Teller. The first one, and this is typically the one which is dominant, and this is the band gap. So it means when you reduce the band gap in your system, the pseudo Jahn-Teller starts to be more important because it's in the denominator. And if you will go to zero, if the band gap would be zero, this will go to infinite, and then that's another example why the Parallels distortion, the metallic states cannot exist, because it will be unstable because of this goes to zero. Okay, so this is the first term which basically define the strength of pseudo Jahn-Teller. And there is another one which is this electron-phonon coupling. So now if you look at in our just to look at in experimental data, what is important to realize is that now if I look at the band gap, what you find, how it's evolved is number of units, and here I mark the transition when happened. So you see that the transition happens in the stage where basically this band gap is already constant. So it means that at the beginning, if I have a short change, of course the band gap is going down, so I'm increasing the pseudo Jahn-Teller transition, but then it remains constant. So it means that this term is not or this parameter is not longer important. So it means that this band gap variation is not the reason for the phase transition. So the second one is actually this term which happens here. Okay, and now here it's instructive, for example, to look at this phase transition in terms of like DFT. I mean the simple DFT. Of course, if you do the simple DFT, we will not be able to predict where exactly the phase transition happens. So for example, I think this is the calculation made for PBE0 functional, and you see that we see the phase transition, but not in the unit of 25 monomers, but 11. Yeah. So how to read this one? So this is number of monomers. So we calculated for each monomer, for each system, we calculated the real structure, which consists of 1, 2, 3, 4 monomers, and we are looking actually what is the character of these frontiers orbitals, which I for dimer I plotted here. So I have a HOMO -1, HOMO, LUMO. So these are these 4 states here. And now if you look at this, important is to realize actually what, and I already mentioned, is the character of the wave function on this triple bond. So here we see that the HOMO, the last occupied orbital here, has a bonding character on this triple bond. So I will mark this as a red one. And if I go to LUMO, actually you see there is an anti-bonding character. So there is a nodal plane here on this triple bond. So this one I will plot as a blue. But then if you go to one occupied up, you will find that actually this has opposite character. So we see that these two frontiers orbitals, which I plot here for in the trivial phase, they have a character of this bonding or anti-bonding. However, when you have this phase transition, when you go to this trivial, actually these two guys, they swap. Then we have these black guys here, which are this H state. And here I have a red one. So now this manifold of this conduction bands and valence band then now remains of the same kind. Yeah. So what is important now in this pseudo Jahn-Teller transition to realize to calculate this electron-phonon coupling. And here that's already the strength of the electron coupling could be understood from the principle of the symmetry, because I have this stretching mode here, which is an elongated this triple bond, which is the active phonon mode, which I consider here. And now this will tell you that actually if I have a transition of the same kind, so it means I'm looking in this triple bond here, so means that this electron phonon coupling, it's only available for the same symmetries, you know, and if I have two antisymmetries there, this homo-LUMO transition or this electron phonocoupling is forbidden. So for this reason, if I go to this homo -1 to LUMO, this is the only one, which is where I connect this bonding, antibonding. These are only the ones where basically I have this electron phonocoupling acting. Yeah, so I cannot connect these two guys. So now what happened is, now I can start to calculate these electron phonon couplings depending on the chain, you know, the length of the chain. But now important is to understand that at beginning, okay, these two guys, they don't connect, but now I have a manifold that basically this guy can connect to this guy and this guy can connect to this guy. So when I start to increasing the chain, I start to increasing the chain which are active, this, and not only that, but also I'm increasing this number of vibrational modes which are active, because again, I'm multiplying them. So which is actually seen here. So if I have 5, now I have a 5 vibrational modes or 4 vibrational modes of this stretching. So now I have to assume all of them, and then that's actually this increasing length. I'm increasing basically this kind of electron phonon interaction, and that's what you can see here. Okay, so with increasing number of length, this electron phonon interaction is increasing because I have more and more states which can interact each other. The important thing is that actually at the end, when there is the phase transition happen, this vibronic effect will be gone, because I told you that basically there is no vibronic state or vibronic coupling between the states of different parity. Okay, so here it will be gone. So that's basically the explanation of this first part. Yeah, I see I'm really long. Sorry for that. So yeah, just say this. Now we can synthesize this topologically non-trivial phase, and we can really track down what is the origin of this electron phonon transition, or this quantum phase transition driven by electron phonon. Okay, so I will go to the second part, and probably here I will skip this condo because then it will be very long discussion, and maybe we can then discuss privately if you are interested. So here I'm going to refer to the recent work in collaboration with this Lu Jiong and Wu Shan from Singapore University. So idea here is, I already mentioned, typically when you look at these radical molecules which are based on these properties of biparticle lattice or electron-electron interaction, you at one moment you are stuck, and you typically work with biradical systems. But now idea is, okay, we may combine both. So we can combine the strategy to use the topological frustration electron correlation. So in Singapore, they prepare the precursor and they synthesize on surface these molecules. And actually these molecules has a both. So it has basically this topological frustration, which introduces 2 ampere electrons, and on top of that, there is also effect of electron-electron correlation, which gives rise to these 4 ampere electrons, and it's very strongly correlated system. Sorry. So now this is the molecule. I said the precursor comes from the Wu Shan. So from Singapore University, and then the group of Lu Jiong, they put the molecule on the surface, they anneal it, and then they got this very nice, what we call butterfly molecules. Now, if you look at this molecule, there is a signature, a very low energy bias features the spectra at, let's say, 10 milli or 9 millivolts, which we can tentatively, or people in this business, we tentatively attribute to the spin excitation from the ground state to the first excited state. Okay, so again, here to address this molecule, you can start with very simple Hickel theory, which tells you that if you just choose this one electron picture, you will see that already you have two zero energy states, which comes from this topological frustration of this biparticle lattice. So there are 2 states which separates each on different sublattices. And then on top of that, we have 2 states, the homo-LUMO states, which are reasonably close. So now what then the theory, like if you use this Hubbard model to solve this problem exactly, it tells you actually that now what you will get is many-body ground states, which is not composed just one single determinant, but you have strong contribution of other configurations in your ground state. So what if you do DFT calculations, you will again get this singlet ground state, but then the spin excitation to the first excited triplet state is about like 150 millivolts, which is far from the experimental value, which is 9 millivolts. So now when we do this CASCF calculations, we can get, and including some dynamical correlation, we can get close to, very, very close to the experiment, like 9 millivolts difference between singlet and triplet. And we can also, from this CASCF, or which is nothing else than exact diagonalization in this molecular active space, we can also get here the signature of number of unpaired electrons, which somehow tells you that we have 4 unpaired electrons in the system. What is interesting now, you can look at also, theoretically, we have 4 unpaired electrons, and you can look how they are organized. So we can use this representation of maximally localized natural orbitals, and then each of them will represent one spin in the corner. And then you can calculate also the spin-spin correlation between them. And what you will find that on one of these edges, they are ferromagnetically coupled, and on the other hand, they are antiferromagnetically coupled on the other side. So that somehow reminds again the spin, the difference, presence of the difference lattice A or B on these edges. Okay, so now you can also look at this spin excitation or these maps at 9 milli eV, and to address it experimentally, I mean, you can see this is the EV map taken experimentally, and to mimic somehow this map of spin excitation, what we use here, which is called in chemistry transition measure orbitals, which is nothing else, because you know there is one fundamental problem. I mean, when orbitals are not observable, so always when we look at the STM images, how the chemist would say, how you can say that you observe the orbitals. So, and he is right, orbitals are not observable. So if we look at this STS, we are looking to some transition. So for each transition, you have to define your kind of orbital representation. And this representation in this case is this what is called transition natural orbitals, which is nothing else that basically you apply this operator or spin flip operator on your ground states to drive it to this first excited or second excited states. And that's actually the concept of natural orbitals. If someone is interested, please look at this reference. And indeed, so we adopted this one here, and you can really, you know, because we know the ground state is many-body ground state and the first excited states, and these are the results. And I think the comparison with this experimental value or experimental map when we use this natural transition orbitals is pretty good. Okay, but one fundamental thing now is I told you that this is the tetraradical. We see some spin excitation, or we see some inelastic signal at 9 milli eV, which nicely coincides with the calculated value between singlet and triplet. But of course, still you can argue that, well, I'm still not convinced that this is the magnetic system, yeah, because what is the experimental evidence? You know, one possibility would be, and that the people already tried for other molecules, okay, if this inelastic signal is magnetic origin, if I put magnetic field, this system or this spin excitation should change according to the Zeeman splitting. But of course, for that you would need very high magnetic field, which is not available in our microscopes. So we have to look to that, or we need to search for different kind of direct experimental proof that this is indeed magnetic. So for that, we use the technique where we functionalized it with a niclosine. So this is the molecule, this is double-decker molecule, 2 pentadienes and nickel in between. The nice thing about this niclosine is a spin 1, and it has certain magnetic anisotropy. So the triplet state is split to this m equal to 0, and then by magnetic anisotropy, which is about like 5 or 4 millieV. And then nice thing about that is that also it has very, very strong spin excitation. So that's indeed here you see that when you record this DIDV map, you have very pronounced peaks around this 4 or 3 millieV, which corresponds to this magnetic excitation from this MSZ0 to MSZ1. Okay, and that was actually developed in the group of Limon in Strasbourg already, and they've shown some features. So now what we're gonna do here, we will functionalize the tip with a nickelocene, and just to make, and what we're gonna do is we will just approach towards to the molecule and see what's gonna happen with the signal. So when you do it on bare surface, when we start to approach, you see that the peak remains more or less constant, just the intensity is increasing. However, now when we go to this butterfly molecule and when we approach on this edge state where the spin supposed to reside, now you see that actually this peak here starts to shift strongly, and then we see another spin signal here, which I will discuss in a minute. So to understand this, what we can do is now theoretically we can establish the model, the spin Hamiltonian, Heisenberg Hamiltonian, where there is a Heisenberg interaction between the spin of the nickelocene as equal to 1, and now this tetraradical molecule, which we represent with, let's say, this model. So now you can take this Heisenberg model, you can approach close to each other, and now increasing this exchange coupling between these two spins, you will start to see how this energy is, how this excitation spectrum of Heisenberg model is evolving according to increasing J. So what you see, there is a ground state, so both nickelocene and molecules are in the ground states. Then you have a first branch which corresponds, the molecule is in ground states, in singlet states, and the nickelocene is in excited states. Then I have then I have another one which nickelocene is ground states and molecule is in excited states, and then I have this branch where both are in excited states. So when we published this, basically we were just using very simple approach and say that this one we are not seeing here, and actually what you see is only this and this one. Now, and that somehow when you plot it here, that actually reminds very well what you observe in the experiment. Now we develop, also we add on top of that the co-tunneling theory. So basically now we can also calculate the transport base for these systems. And indeed there you see that this kind of branch is kind of silent because depends on the coupling of the spin with the tip. Yeah, so it's not involved.
Could I interrupt you?
Yeah, sure.
In magnets, there are sometimes magnets, they couple with phonons and form hybrid modes. Is it possible to have something similar here? So these magnet excitations, with milli-electron volt energies, and I know there are some modes that originate from acoustical phonons because of the finite size effects. Will be they? Is it possible if they were in the same energy range, and could they couple?
Well, typically, I would say, if you look at phonon modes, I think here for this butterfly molecule, I know that if you have an acoustic branch, then you go very low frequencies. But typically, if I look at the molecules, there, these frequencies start to be more high energies, because typically, for example, when we have a CO molecule on the tip, so there is very weak frustration mode, which is around like 3 millivolts, and this is the pendulum mode. But here, that's very, very soft mode. Here, typically like CH bond, these are very far enough. They are very far in energy. So I mean, we do not calculate the vibrational modes for this molecule, but I would expect that there is no modes around like 10 milli eV or something like that. So I'm not sure if there will be some vibrational mode which would be able to couple to this. Yeah.
Okay, thank you.
You're welcome. Okay, so well, I think I will stop here because we are already a little bit out of time. I just want to very briefly mention, and if someone is interested, please look at to this reference. So because now it's interesting to look at these molecules, and they also feature just advanced. This is the radical molecule, and they feature the Kondo effect. So of course, Kondo effect typically is related to it's well understood for system 1/2 spin, but now there are many examples where the molecules with high spin state, they can also feature the Kondo state. So I mean, I would just say that we recently developed the theory for this multi-orbital Kondo screening, which could be applied for this molecular high spin, for this Kondo signature observed in the high spin molecules. So with that, I will jump through because that will take time. And well, I would like to thank you a lot for your attention and also for the invitation.
Okay, let's thank Pavel for great talk. Do we have any questions? Please just go ahead and ask. Please just unmute yourself and let me ask. For this SCCH chains, so is it possible, to build many chains, to couple them, to engineer some electronic structure? How these localized modes can be used? So what can be built from them, or?
Yeah, that's a good question. I'm not sure because if that could be used for some computing, not completely sure. I know that now people, they investigate these modes, how they shine light, but I'm not sure if there's any perspective for any like quantum computing, what people have been talking for these topological states in these quantum wires. I don't think so. This is the case. I think it's more like honestly, I was never thinking about like the direct application. I was more thinking about like this basic science, to understand what's going on here.
Okay, thank you. Any other questions? Please just go ahead and ask.
Okay.
No brave people today.
Maybe it was too far from you guys.
Alex is missing, and we don't have many questions. Okay, so in this case, let's thank Pavel again.
Okay, thank you very much for invitation. Hope to see you one day, guys, in presence. Okay, thank you.
And see you in a month.
See you. Bye.